Section 3.4 is called zeros of polynomials. So we're going to take a look at a theorem that's going to help us find the possible rational zero. So it's called the rational zero theorem. So if f of x, which is denoted by all of this stuff right here, just means it's a polynomial, where a sub n is our leading coefficient times our largest degree or our largest power of x, and then it keeps going down, and then a sub 0 is our constant. So if f of x is this polynomial function, and it has integer coefficients, so the a sub n minus 1, a sub n minus 2, all the way down to a sub 1, and then a sub 0. They're all integer coefficients. And that our leading coefficient isn't 0. And if, and I'm going to explain this, p over q in lowest terms is a rational zero of f, then p is a factor of the constant term. So we get p from the last number here, and q is a factor of the leading coefficient a sub n. So we get q would be factors of our very first term. So anytime we want to find the possible rational zeros, it's just equal to p over q, which is the factors. We want to include plus or minus because they could be positive or negative. Factors of our leading coefficient, of our constant term rather, over plus or minus the factors of our leading coefficient, a sub n. We really only need to keep one plus or minus sign in front of all of them. So let's take a look at some examples. So we want to list all possible rational zeros of f of x is equal to negative 2x to the 5th plus 3x squared minus 2x plus 10. So what we first want, p over q. So p is going to be the factors of our constant term of 10 divided by our factors of 2. Now we could ignore the signs because we're going to keep plus or minus signs all over these. So we could just put plus or minus. So factors of 10 are 1, so we could do plus or minus 1. 2 goes into 10, so plus or minus 2. 5 goes into 10, so plus or minus 5. And then 10 goes into itself, so plus or minus 10. Factors of 2 are just going to be plus or minus 1, and then plus or minus 2. Now we're going to go through and divide all of these. And anything that repeats, we just sort of, we kick out. We only want to write them once. So what I'm first going to do is take plus or minus 1. So all of these are going to get plus or minuses in front of them. 1 divided by 1 is 1, so we're going to have 1 plus or minus 1. Then I'm going to do 1 over 2, so I'm going to have plus or minus 1/2. So I divided 1 by 1, then 1 by 2. Next, I want to divide 2 by 1, so that's plus or minus 2. Now 2 divided by 2 is 1. We already have that, so I don't have to do that again. Then I go 5 over 1, so we're going to have plus or minus 5. 5 over 2, so we have plus or minus 5/2. 10 over 1, so I get plus or minus 10. And then 10 over 2 is 5. We already have that. So these are my list of possible rational zeros. And most of the time, because this is going to be a lot of numbers to try if we have to go a little bit further, most of the time I'm just going to ask you to list the possible rational zeros. Now, in this next problem, we are going to, I want to take you through a step of how we could use the possible rational zeros to actually find the zeros. So our function here, f of x, is x cubed minus 4x squared plus 3x plus 2. So first we want to find the possible zeros. Again, we call them rational because they're all going to be rational numbers. Rational numbers just mean if we see a number in decimal form, it's either going to end or repeat. So that's going to be p over q. So we're going to have p, again, is going to be the factors of 2. So we have plus or minus 1, plus or minus 2. Q is going to be the factors of the leading coefficient, which is 1, so we just have plus or minus 1. So this list is much smaller, a lot shorter than the previous one. So if we divide 1 divided by 1, so we get plus or minus 1, and then 2 divided by 1, so we have plus or minus 2. So we only have 4 possible rational zeros. So it's not hard to test these to see which ones are the zeros. So now we're going to use synthetic division. I'm going to start with positive ones, so I'm going to put that on my shelf. And then I'm going to write out the coefficients. Remember, if we get a remainder of 0, then that number is a 0 of our function. So I'm going to have 1, -4, 3, and 2. So we'll go through this. Get a lot of practice with synthetic division in sections 3.3 and 3.4. So we'll bring down our 1. 1 times 1 is 1. -4 plus 1 is -3. 1 times -3 is -3. And we get a 0. 1 times 0 is 0. We get a 2, so it's not this one. So 1 is not a 0 of f of x. All right, let's try -1. Again, we'll bring down the 1. -1 times 1 is -1. This will give us a -5. -1 times -5 is 5. 3 plus 5 is 8. -1 times 8 is -8. We get a -6. So -1 is not a 0 of f of x. Let's try positive 2. So start with the 1. 2 times 1 is 2. Then we're going to get a -2. 2 times -2 is -4. Then we're going to get a -1. And we get a -2. And we get a 0. So we found one. So 2 is a 0 of f of x. We do have to try the last one. We'll do a -2. So here we'll get a -2. They'll give us a -6, 12. We'll get a 15, a -30, -28. That's not a 0. So the only value that is a 0 of f of x is 2. So we can write it this way. So we know f of x, if 2 is a 0, then x minus 2 is a factor. And then what's left over is, and again, we started off with x cubed, so we're going to go down to x squared. So I'm going to have an x squared, 1x squared, minus a 2x minus 1. And then we could find the remaining zeros this way. So we know it factors. This already gave us our factor. We can't factor this, but we have to use the quadratic formula. So we want to solve for the remaining factors. Or rather, remaining zeros. So this one here, I'm going to use a quadratic formula. So we're going to say x equals the opposite of b. So we're going to get 2 plus or minus square root b squared would give me 4. Minus 4 times a, which is 1, times c, which is -1, all over 2 times a, so that's 2. So we're going to get 2 plus or minus. This will give me a 4 plus a 4, so we'll just get radical 8, and we'll simplify that radical 8 into 2 radical 2, and dividing all of that by 2, so we get 1 plus or minus radical 2. So all the zeros are going to be the 2 that we found when x equals 2, then 1 plus radical 2, and 1 minus radical 2. Now that was a lengthy process, and that was just for 4 zeros, or 4 possible zeros that we found. So again, on any kind of test, activity, quiz, I'm not going to ask you to do anything more than this. If there were more possible rational zeros, I'm just going to have you list them. All right, let's take a look at another theorem. This one is called the fundamental theorem of algebra. So This theorem says if f of x is a polynomial of degree where our degree is going to be greater than or equal to 1 with complex coefficients, remember complex numbers of the form a plus bi, then f of x has at least one complex 0. And that's what we can figure out from the degree. This tells us how many complex zeros a polynomial function has. And it's really this next theorem that we're going to use quite a bit. It's called the conjugate zeros theorem. So this theorem says if f of x is a polynomial with real coefficients, and if a plus bi, so that's a complex number, just as long as b isn't equal to 0, is a 0 of f of x, then its conjugate a minus bi is also a 0 of f of x. So if you need to, pause the video so you can take some time to copy down these theorems. And we're going to jump into an example that pertains to these theorems right here. All right, so let's say we have our polynomial function. F of x is going to equal x to the 4th minus 6x cubed plus 28x squared minus 18x plus 75. And 3 minus 4i, we're being told, is a 0 of f of x. We want to first find the remaining zeros. So that means if 3 minus 4i is a 0, we're going to use synthetic division, and we're going to put 3 minus 4i on that shelf. We're going to have 1, negative 6, 28, negative 18, and 75. We'll bring down the 1. So we're going to get involved with some complex numbers here. So 1 times 3 minus 4i is just 3 minus 4i. Well, negative 6 is a real coefficient, so I'm just going to add that with my 3, so I'm going to end up getting negative 3 minus 4i. Well, now I need to multiply 3 minus 4i times negative 3 minus 4i. So I'm just going to do this off to the side. So this will give me negative 9. On the outside, we'll get a negative 12i. On the inside, we'll get a positive 12i. And last, we'll get a plus 16i squared. So the 12i's are gone. I get a negative 9 minus 16, so we're going to get negative 25. So that is what this number is going to turn into. 28 minus 25 is 3. When I multiply 3 times 3 minus 4i, we're going to get a 9 minus 12i. So now negative 18 plus 9 is negative 9 minus 12i. And then I need to multiply 3 minus 4i times negative 9 minus 12i. So that's why we had to practice these types of problems a lot. 3 times negative 9 is negative 27. Then we'll get a minus 36i. In the middle here, we'll get plus 36i. And then plus 48i squared. 36i's cancel out. We have negative 27 minus 48, which actually gives us a negative 75. So that will go here, and we get 0. And what this allowed us to do is figure out the other coefficients right now. So from that the last theorem we were looking at, the conjugate zeros theorem, that if 3 minus 4i is a 0, 3 plus 4i will also be a 0. So we're going to continue this process one more time. But now we're going to use these as our coefficients. So we've got 1, negative 3 minus 4i, 3, and a negative 9 minus 12i. And we're doing this because this would just be the next polynomial that's left. So I'm going to bring down the 1, and then we'll get 3 plus 4i, which is nice. This will give us a 0. And then this will just, 3 plus 4i times 0 is just 0. So we'll get a 3. And I multiply this, and I'm going to get 9 plus 12i, which gives me a 0. So now, we'll go ahead and write out that f of x is equal. So this right here will give me, because when I started off with x to the 4th, this one would be an x cubed right here. So now this would be an x squared. So I could write this as factor of x squared plus 3. And then my 0 up here, I'm going to have x minus the quantity 3 minus 4i. And then I'll have x minus the quantity of 3 plus 4i. So now what I could actually do is just take all these factors. So this would be if you were asked to write this in factored form. And then I can get my other zeros here. So we'll solve x squared plus 3 equals 0. We know these other two just kind of comes from x minus the 3 minus 4i, and then x minus the 3 plus 4i. So here, x squared is going to equal negative 3. X will equal plus or minus the square root of negative 3. So x equals plus or minus I radical 3. This one over here, x would equal as 3 minus 4i, if I were to add that to both sides. And then over here, x would equal 3 plus 4i, again, if I were to add that to both sides. So the zeros are, we can do negative I radical 3, positive I radical 3, 3 minus 4i, which was given to us at the very beginning, and then 3 plus 4i, which by the conjugate's theorem we would know. All right, something else we're going to go through is something called a rule of signs to figure out how many positive real zeros we have, how many negative real zeros we have, how many non-real zeros do we have. And there's this little rule named after a mathematician, Descartes. We call these Descartes' rule of signs. Okay, so this rule starts off with us letting f of x be a polynomial with real coefficients and a non-zero constant term. Then to figure out the number of positive real zeros, all we do is we count how many times the signs change from positive to negative. So the number of positive real zeros is either the same as the number of sign changes in f of x, and again, feel free to pause the video as you go through this, or less than the number of sign changes in f of x by a positive even integer. And just wait for the examples. This rule will make sense. The number of negative real zeros is either the same as the number of sign changes in f of the opposite of x, or it's less than the number of sign changes in f of negative x by a positive even integer. So let's apply this rule. We're going to determine the number of possible positive and negative real zeros. So let's look at f of x is equal to x to the 5th minus 6x to the 4th plus 12x cubed minus 12x squared plus 11x minus 6. All right, so all we have to do for possible positive real zeros is just count the sign changes. So our first coefficient is positive, so we have a sign change here. We have a sign change here. Changes signs again, again, and again. So we have 1, 2, 3, 4, 5 sign changes in f of x. So we're going to make this little chart off to the side. So we're going to start positive real zeros. We could have 5, or it can go down by a positive even number, so that would be going down by 2, so we could have or 3 or 1. I'm going to come down here for negative. So first I want to figure out f of negative x. So that's going to become a negative x to the 5th minus 6 times negative x to the 4th plus 12 times negative x cubed minus 12 times negative x squared plus 11 times negative x minus 6. So because this coefficient here is a -1, when I take negative x to the 5th, I just get negative x to the 5th. This part will still say x to the 4th, so we get minus 6x to the 4th. This will become a minus 12x cubed. This part will stay the same because I'm squaring it, so I get a minus 12x squared. Then we'll get a minus 11x and a minus 6. So if you take a look here, this is negative, that doesn't change, it doesn't change, doesn't change, so it doesn't change. So we have no sign changes in f of negative x. So there are no negative real zeros. So I'm going to go back up to my chart. We'll say negative real zeros. And then we want to kind of finish this as well. So then I'm going to put the number of non-real zeros. And then we need a total. So if I have 5, and I know I have no negative real zeros, this has to be the difference because my degree is 5. So I would have to get a total of 5. So I need to get 5 all the way throughout here. So if I have 5 and 0, there's no more left. I can't have any non-real zeros. Here if I have 3 and I know I have no negative real zeros, well the only way to get to a 5 is going to be if I have 2. And here if I have 1 real positive real zero, I'm still going to have no negative real zeros. I need a 4 to get to a 5. So the degree tells me what the total number should be. So this is just one scenario. If I have 5 positive real zeros, I have no negative real zeros. We found that out. That means I can't have any other kind of zeros. If I have 3 positive real zeros and no negative real zeros, that means I have to have 2 what we call imaginary zeros to get 5, because 3 plus 2 is 5. If I have 1 positive real zero, and again we know we have no negative real zeros, I would need 4 imaginary or non-real zeros here to get to 5. And let's try one more example. So here we have f of x is going to equal 2x to the 6th minus 5x to the 4th minus 3x cubed minus or plus 7x squared plus 2x plus 5. So if we take a look here, we've got a sign change here, and it doesn't change again until here, and that's it. So we only have f of x has 2 sign changes, therefore 2 positive real zeros. Let's find f of negative x. That's going to become 2 times negative x to the 6th minus 5 times negative x to the 4th minus 3 times negative x cubed plus 7 times negative x squared plus 2 times negative x plus 5. So negative x to the 6th is going to turn back into x to the 6th. So we get a 2x to the 6th. Same thing here. Negative x to the 4th is going to turn back into x to the 4th. So we get a minus 5x to the 4th. Now over here, negative x cubed will become a negative x cubed. So that negative times negative 3 turns into a positive 3x cubed. We'll still have a positive 7x squared because squaring this is the same as just x squared. Then we'll get a minus 2x plus 5. So let's count the sign changes here. We've got 1, 2, 3, 4. So f of negative x. So f of x has 4 sign changes. All right, so we're going to make our list here. So we have positive real zeros. We have negative real zeros. We have non-real zeros. And then we'll get our total. All right, so for the positive real zeros, we could start off with 2, or we can have 0, because we go down by a positive even number. For the negative, we can have 4, we can have 2, or we can have 0. Now we have to have 6 for the total because our degree is 6. So for this first column, if we have 2 positives, 4 negatives, that leaves us nothing here for the non-reals. Now if we have no positive reals and we have 2 negative reals, that means I need to have 4 non-reals to give us 6 here. Now to fill in this other combination, if I have 0 here, I could still do, we need all these combinations, so I could still say, well, if I have 2 positive reals, so this is starting like another scenario, if I have 2 positives, I'll look at each one here, no negatives, then I still need 4, so we get a 2, 0, 4, that's still going to give us 6. So now I can have all these combinations. So I have the 2 with the 4, I've got the 2 with the 0, I've got the 0 with the 2. We have to try 0 with the 4. So we'd have 0, 4, and then this would give us 2 to give us our 6. Or I could put the 2 with the 2. And that means I would have to have 2 more here as well to get 6. So we've got a 2 with the 4, we've got a 0 with the 2, we've got 2 with the 0, we have 0 with the 4, we have 2 with the 2, and our last one, I think, is going to be our 0. We have 0 positives, 0 negatives, and then all 6 would be right here. So sometimes you have to look at all your combinations. So you could have 2 with the 4, which will leave us with 0 non-reals. How many different ways can you do 4, 2, and 0 with a 2 and a 0 here? So that would be it.